Hey guys, today we're looking at the concept development practice page 34.2, so make sure go ahead and find that. Units and formulas are starting to get a little bit complicated, so if you have some scratch paper or maybe want to jot some things down on the back side of that summary page, I just kind of want to maybe put all these formulas in one place. So current, and I'm going to put the unit with it in parentheses. Okay, so current is in amps, and that is how much electricity is flowing, or how fast the electricity is flowing. So that is the charge in coulombs divided by time in seconds. All right, so there's one very important formula. And we also have this one, voltage, which remember is a difference in potential energy measured in volts, equals that current measured in amperes times resistance, which is one of those that has a cool unit, measured in ohms. If you wanted to write it out, you would write OHMS, ohms. Okay, but then this worksheet we're bringing in back that idea of power, which I talked about a little bit in the last video, but let's just think about this for a second. So power, its original main definition has not changed. Okay, so power we learned to be work or energy converted, energy transformed, divided by time. Sorry, power is measured in watts. Work's measured in joules, and time we generally measure in seconds, right? But when we're thinking about power in terms of, how much stuff we move, remember work is moving stuff, power is in how much stuff we move divided by time. Well, the moving stuff, that's current. Okay, so I can kind of do a little bit of substituting here and also think about time. Okay, so the bigger the difference in charge, the larger the voltage, the less time it's going to take. So I can do a little substituting here and say, well, power would also equal current, still measured in amps, times voltage, measured in volts. So remember, so it's work, which is moving stuff. Current is how much stuff is moving, how fast stuff is moving. And voltage would make the time less. So that's why it's multiplied instead of by dividing. So I can calculate power as work divided by time, or current times voltage. So now I can get a little even more math crazy, and I can have a third way to think about power. And I know that current is charge moved per time. So I can substitute that in here if I wanted to. So I can have charge in coulombs. And remember, we're substituting charge divided by time in seconds times voltage in volts. Oops, can't see that. So can calculate power three ways. There's one way we can calculate power, there's another way we can calculate power, and here's a third way we can calculate power. So if your question is asking you for power, you've got lots of options in terms of, okay, well, what do I need to know? What do I still need to try and find out? Okay, so again, if you didn't write those down, I would encourage you to pause and write down all three of those formulas, well, really 5 formulas, if you will. And then we're going to go look at this page a little bit. Okay, so they're kind of going through the same thing. I just always think it's easier to understand things if you wrote them down yourself. So power is energy converted per time, or it's voltage times charge per time, or charge per time, or voltage times current. There's all these things. I'm not going to do every other on this one. I'm just going to do a handful of the ones that I kind of think are a little more tricky. so you can see them worked out. So this is not a question, this is just kind of a refresher. The unit of power is the watt or the kilowatt. So remember, there would be 1,000 watts equal to 1 kilowatt. So you may need that information a little bit later. And so then, of course, we have power in watts equals the current times the voltage, where 1 watt is 1 ampere times 1 volt. All right. So I do think that 1, 2, 3, 4 you're going to have no problem with given those equations. Just pay attention to your units. We're going to talk about 5, 6, and 7 a little bit. So the equation power equals energy converted divided by time. They just want you to rearrange this equation. So if I wanted to rearrange this so that energy converted was by itself, what would I do with power and time? Divide, multiply, whatever, and that's what you will write right here. I'm going to kind of talk about 6 and 7 a little more in depth. So explain the difference between a kilowatt and a kilowatt hour. Okay, so they look kind of similar. If you think of this dash as a time sign, it's going to make a little bit more sense. So kilowatt is a unit of power, okay, which remember is a how fast is this machine, this device, using energy. Okay, remember how power is always how fast or the rate of energy use or energy conversion. If I look back at my equation for power, okay, so imagine instead of watts here I had kilowatts. It's an acceptable unit of power. So I have kilowatts here and time here, but instead of seconds I had hours. So if I have, remember, power equals work divided by time. If I used kilowatts equals work, I'm going to leave that blank for a second, and then hours, okay, and then I'm leaving this blank intentionally. If I solved for this unknown thing on the top here, I would take kilowatts times hours, right, because my unknown is divided by hours. So this is a unit of energy, of work done, called the kilowatt, hour. Okay, so you find a kilowatt hour by taking kilowatts of power times hours of use. And they usually frame it as being per 1 hour of use, but the idea is you're taking kilowatts of power times hours that it's used, and that's how many kilowatt hours of, again, kilowatt hours is a unit of energy used. Okay, it's not a unit of power. Kilowatts is a unit of power, and it's not a unit of time. Hours is a unit of time. Kilowatt hour is how much energy is used. So we're going to work through 7. On tomorrow's assignment, you're going to do a bunch of these more on yourself, so I don't feel bad just walking through this more difficult one today. So one deterrent to burglary, if I could speak, is to leave your front porch light on all the time. If your fixture contains a 60-watt bulb at 120 volts, and your local power utility sells energy at 8 cents per kilowatt hour, how much will it cost to leave the bulb on for the whole month? Show your work on the other side of the page. So I kind of worked ahead just a little bit and wrote down all the things out of that question that we need. Okay, so things we know. It's a 60-watt bulb. My outlet is 120 volts. I'm getting charged 8 cents. There's the 2 ways to write 8 cents. Per kilowatt hour of energy use. Remember, kilowatt hour is a unit of energy. We're going to say that a month is 30 days. I know that there's 31-day months, and I know that there's a 28-day month. We're going to go with 30 days here. So, now what? All right. So we need to figure out how many kilowatt hours of energy would be used in 30 days of time. Okay, so if I go back to how do I figure out kilowatt hours, it is kilowatts power equals kilowatt hours work divided by time, and this time in hours because we're going to a kilowatt hour, right? So it's 60 watts bulb, but I need kilowatts, right? So to get to kilowatts, where I said there's 1,000 watts in 1 kilowatt, so that would be 0.06 kilowatts. Okay, so that's the power of the light bulb in kilowatts. So I remember power equals work divided by time. So that 0.06 kilowatts is my power. The work is the energy that is converted, so that is what I don't know. Question mark kilowatt hours over time. And we could do this a couple ways. I'm going to follow the standard that we usually calculate for 1 hour. Okay, so in 1 hour of time, let's do it the easier way. Okay, so let's figure out how many hours would be in a whole month, and then we can figure out directly how many kilowatt hours. So we said there's 30 days in a month. We're going to figure out how many hours that is. We know there is 24 hours in 1 day. 30 and 24 are both on the top. That gives us 720 hours of time. So I can put that 720 hours right here. If I multiply that over, that'll give me kilowatts times hours, or kilowatt hours. So I go 0.06. 0.06 times 720 gives me 43.2 kilowatt hours of energy. So is it going to charge me $43.20 for every month that I leave that light bulb on? I hope it doesn't cost $43 for every light bulb in my house. Okay, so I've got one more piece of information I still need to use. It says the utility charges 8 cents per kilowatt hour. Okay, so I need to take this number times 0.08 to turn that into dollars, or I could take it times 8 and turn it into cents if you want to know how many cents it takes, but I think most people are probably more familiar with dollars. I'll take that times 0.08, I go 43.2 times 0.08, so for leaving that one light bulb on 24/7 for a month would cost $3.46 about. Okay, so hopefully that seems like a reasonable answer. If you would please do 1 through 5 on this page. It'll be kind of a short one, but we've got a big math assignment coming up tomorrow. So 1 through 5 here is your assignment. Please take a picture and put it on Classroom. If you could zoom in as much as you can just on that 1 through 5, it would make my life a little bit easier. Thank you.